So here, please work for us. So yeah, come and have a look, because it was a shame to miss this. We ran it a moment ago and it worked okay. Back one.
Can I exit the presentation and take video?
Oh, trouble with this. Right. It is a video. Oh, we're really lost. No, you're way, you jumped far ahead. It's going to be a very interesting presentation now. What have you got there? It's that one. Right. Go back to the original file. Yeah. Go into, what do we go? Basically, insert. Okay. Video. This device. Yeah. Right. And then search down here. Find it. It's called Pendine. Keep on going. No, go on. Keep on going down.
Well, what's that about? Yeah, we can find it. Go on, keep on going down. Yeah. What's that? No, up. And down, it's this one. Up one. Up. Right, this is very important. You're going to see this, right? Okay. Thing is, when we start. That is 0 to 820 miles an hour in 0.8 of a second. Okay, so running 40 G. Okay, so we've got all this done, and now the great moment came when we did about 13 of these, and the great moment came when we had to compare that with the CFD, and that's the original document and the original graphic, and we've got a straight line correlation between the two, and suddenly we realized we could do it. And so we've got to push on hard, get ahead of McLaren, who gave up, and way people through. So there's the car called Thrust SSC for supersonic car, driven by a very brave guy called Andy Green. And as you can see in the general layout of the car, the two big Spey engines, so it gives us 44,000 pounds of thrust. We've got the long, thin nose to minimize the shocks. The engine, the cockpit is in the middle between the engines, and then you've got the long tail at the back. And one of the problems we had was that we got to make it, we had to ensure that we got the best aerodynamics to it. And that meant that we couldn't steer the front wheels. Front wheels were obviously going to do that, and we couldn't steer. So we'd have to steer the back wheels. So the car's rear wheel steer. Right, so here we go, and we're going to run. And this is a hell of an experience. Is it going to work? I'm sorry, it's doing the same thing. Isn't this fun? Right, let's go back to the do what I did before. Fun. Insert video. Yeah. This device. Yeah. Yeah. Right. There we go. Experience. Because we've got a car here running at supersonic speed. I'm very brave man driving it. I think we're on the Black Rock Desert in Nevada. And you can't hear it. You can't hear it because of course it's being fast inside. Until it comes up alongside you, you get the shockwave. Shockwave.
I'll say that was fast. Okay, Cuba. We got it. Everything is being wonderful. That's a seed for stop. 15.5.
Exit copies. Exit station standby. SSC has stopped mile 13.5.
So there it is, an 11-ton car with 100,000 horsepower. Typical Formula One car's got about 1,000 horsepower, so it's about the same as 100 Formula One cars. A great drive by a very, very brave man. This was very interesting because we had a number of microlights in the air, and that was one of the famous shots of the car breaking the sunband, the huge shockwave up the front. And that had never been seen before. Fantastic thing. And this is something which I'm really very proud of. This is the American Society of Mechanical Engineers, and they produce basically an award called the Historic Mechanical Engineering Landmark. Very, very few of these in the world. In Britain, we've only got 4 or 5, and one of those belongs to our team. We achieved that. Okay, so then what happens? Well, we moved on. The Americans wanted to move on, and they decided that they were going to have a go. So we decided we would set up a program called Bloodhound, and the idea there was to create the world's first 1,000-mile-an-hour car. So Mach 1.4, that's what we're heading for. There's a huge, huge program. Unfortunately, the entire program was wrecked by the British government, who made us an offer from one of the, which had been put together by the Chancellor of the Exchequer, and they failed to pay it. And then our big sponsor, the Chinese government, decided they were going to drop it. So that was that. So we lost it. But one of the most interesting things is, and one of the most valuable things is, occurred at the meeting we had with the Ministry of Defence. This was a meeting with the Ministry of Defence board, and they were saying we've got a big, big problem in the Air Force, the Navy, and in the Army. The world is becoming very, very much more technical, and we need to recruit kids coming into these services. We need to recruit them, and they've got to have some sort of understanding of STEM. And basically, our education system is not providing what we need. So will you please, they said, set up an education program? So we set up an education program for this, and it became absolutely enormous. We were moving 120,000 kids in UK alone every year. So as a result of this, we got a huge number of engineers, which was very successful, and I'm very proud of it. Here's basically one of the infographics there, Bloodhound Education. It was in 220 countries. Yeah. So I'm sure I've probably got here as well. They produced 25,000 rocket cars and so on. It was an enormous program and a huge success. Now, this is very important to understand. What was actually happening was
here we were doing record breaking, but now this is record breaking with a purpose. The purpose was we can use this for education, and we have no interest in work in progress. We have no interest in our IP issues. We'll make everything available, all the calculations, everything, so they can understand it. The kids can understand it. And this is where you start getting these huge, huge numbers of people. And I like to think we created a very, very large number of engineers. Project didn't go any further, which is a shame because of the British government, but there we go. And what have we got here? I think we got yes, we got the education program.
It's going to be really nice to share our excitement that we've had over the last 3 weeks with the general public. I think they're going to be blown away. It's the fastest racing car on earth, and it feels like it.
I like it because it's really funny and you get to learn like lots of things that are really scientific.
I absolutely loved it today. It's just amazing seeing the car finally run.
So it had a huge effect, absolutely huge effect. And that was the last thing we could do. Because basically at that point it was out of its money and it had to be sold, so on. Now we decided, what the hell are we going to do now? Basically, we've lost that project. Not through our fault, through the wretched government's fault, and so we've got to be very careful if we ever deal with the government again. And so we decided we'd have another go. And we've done all the land speed records, and we still hold the supersonic record. So now we decided we'd try and do something a bit different. And the water speed record is dangerous. So here we go. And of course, this is where I started with John Cobb's boat way back in 1952. And we were lucky because, oh, everything's jumping around now. But if I can't get this going right, there we are. That's what I wanted. We were lucky because we found that John Cobb's team had created another design, and we were able, this was from 1954, we were able to get a hold of the tank model, and then basically, of course, we scanned it, and then basically we started running a jet model.
it seemed to work all right, but it was very sensitive in pitch. Because clearly we were going to have problems with this. So we moved on and we came up with a different design, which is basically this one, which is basically the jet engine down the middle, just like the car, and the twin fins at the back, which give it very good directional stability. The question, of course, is that we had to make sure that our engine worked all right. So there's the engine. It's been very carefully stored for some 20 odd years. And eventually we got it going. So let's just have a look at that. Sorry, we're really jumping around a bit here. Now, is it going to work? Tell me it's going to work. No, it's just going to work. Oh dear, I'm sorry about this.
It's all right.
Insert. Right, let's go back to the video. There we are. This device. Yeah. Sorry, I can't find it. Seem to have lost it. I'm sorry, I had to move on. We seem to have lost that. But we ran the engine up and that's fine. So that's okay. So we got the power and everything. And here's the basic concept of the boat. Now let me just go back to, right, again, this one here, right. Okay, so this is what we're trying to do. And we ran into trouble. The fundamental problem with these boats is that they are hydroplanes and they skim across the water surface. And the problem is they build up high pressure underneath and there's a real danger of takeoff. And if you've seen some of the latest videos of, for instance, Spirit of Guitar, you can see the boats nearly flying. But we're talking in terms of running not at 240 miles an hour, but running at 450 miles an hour. And what we found on development was that the angle of pitch at which the boat will fly goes down to under 1 degree. So it's too dangerous. And I said, we've got to stop this. It's too dangerous. We're going to kill somebody. This is no good. And we were on the point of giving up when a friend of ours came forward with a really interesting concept, which is basically the supercavitation hydrofoil. Now, those of you who know anything about boats, basically, you know, you can get a supercavitating propeller, which will operate at these very high speeds. So this is what we wanted. So you can see here in this particular picture that the engine the jet engine is very important because the jet engine is positioned quite high, thrust line is quite high, and it's actually pushing the bow down. So you can get into terrible trouble if anything happens to that engine. You're going really fast, the lift, of course, is trying to lift the bow up, the jet engine is pushing it down. If the jet engine dies, you will crash. So it's a very, very careful balance. Right, let's move on. And so here we have the typical picture of either a wing or a hydrofoil. And 2/3 of the lift is provided at the front end, at the top, where the flow has to, of course, flow right over a longer distance. The molecules get a bit more separated, low pressure, and underneath you've got the high pressure. So 2/3 from the top up and 1/3 from underneath. But there's a problem called cavitation. So what actually happens is at these speeds, and we're talking about the hydrofoils now, is that once you get up to a speed of around about 70 miles an hour, you get cavitation. And this is causing very low pressure on the upper surface. And basically your lift is lost. So there you are, that's a cavitation. Okay, and you can't go any faster. So the America's Cup guys are stuck with this thing. And the hydrofoils, of course, have been around since 1910. So the technologies were very well known, but they can't go any faster. So what are we going to do? Well, from our point of view, we've got to control the front end of that boat. If the front end of the boat gets out of control, we're going to crash. And somebody's going to get really badly hurt. So we're not going to do that. So we must therefore have, as we suggest, 4 foils, 2 at the front and 2 at the back. Okay, so we can control them. And so let's have a look at the hydrofoils. And it's never been done before. It is actually a world first. Oops, sorry, we jumped to there. There we are. That's one there. The white is the actual foil section, and the red is actually the cavitation and the bubbles and everything else coming off the top. So the lift comes from the underside, and it only operates at very high speeds. So from the boat's point of view, we run the boat up to about 100 miles an hour, and only then do we apply the incidence to the hydrofoils, and then we'll lift up. And we're only lifting up 20 centimeters, so it's just very slightly above the water. And we're very grateful for our friends at Kinetic, who have done all the research on this. They spent 3 years on this, and that's one of the foils running at 450 miles an hour. So we've done all the L over Ds, the lift over drag, and we know that this is possible. Okay, but it's never ever been done before, so we better start finding out something about it. So what we did was we decided, right, okay, we've got to build a model. So just like the thrust SSC, we decided to build a model. So this is our a 10-foot model. It's 25%. It looks a lot like the boat, the car rather, because basically it's the same concept, the twin fins at the back, driver sitting about midpoint, and the heavy jet engine down the middle. And this is a really beautiful thing. And we've got to get running it and get some experience with it. And but it has to be, the fundamental problem we've got with this thing is it's so fast. It'll do 200 miles an hour. It's got a lot of thrust. It's got 350 pounds of thrust, and we can't see it. So you can't have it radio controlled. It's got to be autonomous. We've got to make sure that our autonomous systems are capable of dealing with this. And we're working with Leeds University, who put an enormous amount of effort into this. So here we've got a video, and the question is it going to run? It might do, yes. It's not going on. Just testing. Safe. And then next month, we're going to start looking at these flows. That's when the fun really starts. If we got this thing right, it's to get it right. There we go. And this is where we're going. So there's the performance curve. It starts off where we run it up to about 100 miles an hour, and we bang in the foils at that point, take it right up to 450 miles an hour. And then we go into the deceleration phase, which we do with the foils. We use the foils as a braking effort. We then come off the foils at the bottom, so you can see that slight kink in the curve there. It comes to a halt. 8 miles, that's what it needs. And we'll be running the boat with full afterburner. So we've got to get it built. So what we've got to do is get the model up to 200 miles an hour, which we hope to do in January, February. And then after that, we'll progress there onto the C6, which is the full-scale boat. And the technology here is really quite something, because those foils have to adjust at 100 movements per foil per second. So this is going to be very, very interesting. And we're going to learn, like you guys, we're going to learn an awful lot. So there we are. And thank you.
Thank you so much, Richard, for this inspiring
pleasure.
talk. I think now is the moment for questions, if you've got any.
Go.
Right.
First of all, thank you so much, Mr. Noble, for coming here today and giving us this speech. I just want to say, wow. Okay, the things you've done in the past, not just years, couple of years, decades, absolutely astonishing, amazing. Something I could really look forward to, up to. Now, my question is, so obviously, you've done the impossible practically. What's the type of person that you look for that you want to help you accomplish the impossible with?
Yeah, yeah, you're absolutely right. And this is the fascinating thing because, of course, you've got to get a very, very special collection of people to do it. So the simplest way of doing this is not to recruit. The people who really want to do it and have got the confidence to do it, they come forwards. And then you know jolly well that they put themselves basically at risk. They're going to have a go with this and they're going to join the team. And it's a very interesting way of working because we work as a flat organization. We are non-hierarchical. Okay, so it's not like an ordinary organization, it's a flat organization. Everybody's got their responsibilities and they've got their role and they've got to do the best that they possibly can. Now, what happens here is absolutely fascinating. If they can't do it and they have problems, then they leave. They basically say to everybody, I'm sorry, I can't do this. And literally within days, a replacement person has been found. And the wonderful thing about this is that in this sort of company, you find out who you actually are, what you can actually do, because this is the ultimate. You know, you're part of a team that's going to actually set a record, which, if we can do it, will stand for 40 or 50 years. I mean, this is really something. And you can find out who you are and what you're capable of doing. And everybody in the team will, of course, help you because we're all human and we all fail. But it's a tremendous experience. Now, we've been very lucky with this team because we've started off with recruiting, we don't recruit, they come to us, with our pensioners, people who've just finished their main life's work and now have a pension. And they've come forward and with the knowledge they've got is absolutely amazing. So we've got 3 ex-Rolls-Royce chief engineers, we've got 3 naval architects, the standard is incredibly high. And they're fascinating because nobody's done this thing before. We don't know that it'll work, of course, because certainly kinetics work and all the CFD shows that it's going to work. But is it going to work? We're going to find out. Got a lot to learn.
Thank you.
Thank you.
Question at the top, so just let me walk up.
Thank you for the presentation. The fact you did something like that in the 1900s was very impressive, I think. Like, I would put it above the invention of internet. The fact that you built a car that goes that fast. So recently, me and my friends had an idea, which is the question that, you know, when you build these cars, you put like 48 Gs on a driver that's driving, which is very dangerous, right? But if there was an AI model that could drive your car for you, right? Something like control the launch RPM, and display the throttle curve. You know, if the AI could do it instead of an actual person, would you implement it in your cars?
Now, that's a very good question, and thank you for asking. We've got to make this thing safe. We're not going to kill anybody. We're going to make this very safe. So the full-scale boat is actually going to be, it's going to be autonomous. And we will run it as an autonomous boat until we've got to a point where we're satisfied with it, that it's safe and it works all right. And then we'll put the driver, whether it's a man or a woman, on board. The rules state that the boat has to be driven by a driver. So we have to get that world record, we have to have somebody on board. But there's no reason why we shouldn't develop it as a autonomous vehicle, getting all that data, as you rightly say, in safety, and then finally putting the driver in place. So that's the general idea.
So come to that side.
How do you plan on getting the funding this time?
Yeah, the funding is a terrific battle. It really is. We can't work with people like the banks. We can't work with the basically professional investors. They're all looking for a return for this thing. There's no way they're going to get a return. We'd be very lucky if we pay all the bills and get the job done. So we developed the sponsorship technologies.
And this is absolutely brilliant because basically, providing you've got a big television production, and we're working with Netflix, they're going to get an enormous amount of exposure, and they're going to get a lot of value out of this thing. And of course, it's going to go on for some years, so they're going to get a huge value. So that's really where it comes from. And also, the great thing too is that unlike professional investors, the professional investors always like to get involved in the project. The last thing we want is bankers in the project who really don't. These people don't take the sort of risk level that we take and we're happy with. They don't understand what the hell's going on. So we don't want those people. So basically, sponsorship is how it's done. And it is amazing what people will do. So to give you an idea, we have an aircraft manufacturing company who says to me, right, Richard, we're going to build the boat for you. You've just got to get that model up to 200 miles an hour. That's the proof of concept. And then we will build the boat. We've already been given all the carbon fiber for it, which is terrific. So I'm looking forward to this. But of course, the other thing which I didn't have time to talk about was the education side. And now what we're doing is we're building up relations with lots of universities. And the idea is the universities will each specialize in one particular element of the project and then cover it live as it happens. So for instance, it could be structures, it could be the power plant, it could be the systems. And the whole idea is to actually teach the public how these things work, because they don't know, they haven't a clue. So, and what happens is because we do this, they get really excited and really interested. And normally we'd have we will have a supporters club of generally about between 6,000 and 8,000 people. And they'll be able to come down and see the boat being built and ask all the difficult questions, you know. And it's great because we learn an awful lot from these people. And sometimes people come up with something we hadn't thought of, and you think, thank God for that, you know, because we can use that idea. So it's all about communication on a huge scale. And if we do it properly and we're successful, then basically we're going to get thousands and thousands and tens of thousands of engineers. Because as you saw before, when we did it with Thrust SSC, with Bloodhound SSC, we were going to 220 countries. That's almost every country in the world. So stand by.
I'm interested to know, when you're working with the project so close to the limit and at such a high risk for the machine itself that you're working on, and more importantly, the driver, at what point do you make the call? Do you say, I'm confident enough to run this machine?
Yeah, that's a very interesting situation.
Can I follow up, Richard, on that question? So if you could answer both. I mean, I know you've been on that car. Can you describe your feelings on how you've gone through those speed limits? I mean, 200, 300 miles, and when you reach 700 miles, just as a...
Okay, well, I'll do that first. Driving Thrust 2. Basically, I wasn't any good at it. We started off and we made a lot of mistakes. We started off on the wonderful salt flats, and we used solid aluminium wheels because we're running about 8,000 RPM, and a pneumatic tire is frankly dangerous. So we started off like that, and we didn't get the wheel design right, and it was an absolute nightmare. And the first time I drove it, we went sideways at 90 miles an hour. The next time we went sideways again at 270 miles an hour, and we went about 50 miles into the desert before I could stop it. We had problems with the timekeepers at one stage because we went sideways again and the car was pointing directly at the timekeepers, so they got a bit upset over that. But anyhow, we kept going. Now, the extraordinary thing about it was that, you know, here we were with the car, we put an enormous amount of effort in it, and we were failing. And what we've got to do is we've got to learn how to use it. Now, I've driven that car many times to 260 miles an hour on runways where you've got good grip and you're using rubber tires, but this is something completely different. So we decided what we'd do is we'd do a 400 mile an hour run. And so we put John Aykroyd, who was the designer. Sadly, John is no longer with us, but the man was absolutely brilliant. So we put John in the other cockpit on the other side, and I drove it from the right. And we accelerated down the run, and we got to just over 400 miles an hour, and then we braked. And we came to a halt. John hopped out, and he said he was never, ever going to do that again. We turned the car around, and we said, okay, we're going to do a return run now.
and everything went wrong. The organization was a complete mess. I was sitting in the car. I was angry as hell because it should have been a lot slicker than this. But the time had come to go, and everything was ready. So we started up the engine, and I immediately floored it into max burner, okay, to see what would happen. And what happened was amazing. The car went straight. We didn't have any of these directional stability problems. It just went straight. So that was it. It was quite clear now that the way you drive this car is from start with max burner and right up to your VMAX speed that you decide. Then, unfortunately, it rained in Bonneville. The place flooded, and we had to go home, and that was the end of it. But we knew we'd seen 500 miles an hour, so that was good. And then there were very small runs. We went in 1982. We had a bad accident in 1982, but we learned from that. And in 1983, we went back again. And the run procedure is really very interesting. Remember, you're running on a desert surface. Okay, so it's slightly dusty, but it's not sandy. It's load bearing. So you sit in the car, you wait until everything is organized. You've got our track in front of you, which is just 50 foot wide. Lots of parallel tracks because the car breaks up the surface. So each time you get a fresh track. Each track has got to be walked by everybody to pick up any stones or debris just to make sure it doesn't go in the engine. And okay, you're sitting there, you're waiting for the aeroplane because we have an aeroplane. The aeroplane flies up and down the 13-mile course just to make sure we don't have any stray Americans on the course. And then, okay, we're given the signal to go. Hold the car on the brakes with your left foot, right? All these cars are left foot braking. So, and then max accelerate with your right foot. So you go straight through the detents, straight into max burner, and you're off. And between 0 and 330 miles an hour, it's sliding all over the place. It's like a rally car, but you've got to just keep fighting it and keep it in the line and keep it going straight. But you must not let up with your right foot. It's got to be absolutely flat on the floor. Okay, once you get to 300 miles an hour, the airflows and the aerodynamics seem to stabilize, and it goes a lot straighter. So that's great. So you're sitting there enjoying it. It's quite a ride. You're building up speed till you get to 550. At 550, it gets very interesting because two things happen. You first of all get the shock wave on the top of the engine intake, and you see the shock wave go right the way back between the tail fins. And also, and you go a little bit faster, and you get the big shock wave off the front of the car. The car itself isn't going supersonic, but the airflow is. Okay, so you hold it there, and you get right up to the maximum speed. The maximum speed we got was 650.88 miles an hour. And then you're coming out of the measured mile, and you've got to think about stopping. Now, this is the most dangerous bit of all. So you come back on the throttle, okay, to about 90%, having cancelled the afterburner, and then you press the button on the steering wheel, which fires the brake parachute, and you immediately get 6G deceleration, bang, like that. And your head goes right down, and it's very scary because you don't know quite where you're going. You can't see where you're going, but the car is stable, and you're very quickly down to a very leisurely 400 miles an hour. And at 400 miles an hour, you want to get out and walk. It's incredibly boring after what you've been through. And you see it down to 200 miles an hour, bring the wheel brakes in, and then bring it to a halt. So that's it. Right. What was the other question?
The question is, how do you decide I'm confident enough to make my question?
It's, well, right. You're talking about the first run with the driver on board. Okay. So what we do with the program is that the driver will actually drive the boat from the shore, okay? And we've got video on board the boat, and you can see exactly what you're actually doing. And we gradually build the speeds up until we reach a point where we are going at record-breaking speeds. And then the driver's then got to say, yeah, I feel happy about driving it now. And everybody feels confident, you know, because we've done a number of runs like that. We feel very happy that it's safe, and then that's the point when we put it in and ask the driver to drive. Now, it's very interesting, the driver relations, because to get the driver in the first case, we have to put all the applicants through a 6-month program to find out that we've got the right person. And the understanding is if that person gets frightened or just doesn't want to do it, then he or she's got to leave immediately, and we'll find somebody else. That's our problem. But so the driver can walk away at any time he or she likes.
But hopefully that doesn't happen.
Richard, thank you very much for the nice presentation. Just curious to know, like this speed of 450. I'm not sure whether I'm correct here. This is almost 0.6 of the
Mach 0.6, yeah.
Yeah, 0.6 of the speed of sound propagation.
Yeah,
Yes,
sure.
Yeah. So when you talk about the shock wave, what because it's not yet actually reached already the speed of sound. So where is the shock waves coming from?
At Mach 6, there's just very, very limited shock. Mach 0.6, there's very, very limited shock waves. We don't anticipate we're going to have any real problem at that speed.
Right, but theoretically, if you are to get into the speed of sound,
yeah, the model will the full scale boat will never go faster than Mach 0.6.
Okay.
So we've got to keep it very safe.
Yeah. Okay.
Thank you.
So we'll have the opportunity to talk to Richard. I know it's just the end of the session, and personally, I have a lecture to go to, so that's why. But anyway, he's here. So if you want to have a chat with him afterwards, please feel free. Just go up to the stage. If you want to take pictures or for your Instagram pages, please feel free to do so. All right. Thank you so much for attending. Thanks, Richard, once again for your.
Life skills and ethics, just please stay.
Richard, I think there was a small token of appreciation which I have not mentioned. Hold on.
Thank you. Thank you, Mr. Dean.
بس هيعمل مركب يجيب سرعة ايه؟ هيعمل مركب يجيب سرعة
All right, we've got all the questions.